we've looked at Lilith systems, which is a 3 pi orbital system. Now we want to extend that to look at conjugated dienes and beyond. And the simplest example of a conjugated diene is just 1 3-butadiene. Which has 2 carbon-carbon pi bonds adjacent to one another. It's C4H6, so there are 4 times 4 plus 6 total orbitals. But only 4 of those will be pi symmetry. And the others will be in the plane, because we'll have a 2s, a 2px, and a 2py for each carbon, times 4, that's 12, and then we'll have the 6 hydrogen 1s orbitals. Which means that 18 of those lie in the plane, and then only the 4 2pz orbitals lie out of the plane. And we're only going to worry about the pi system. So what we're going to do is the same thing we did for the 3 pi orbital system, is we're going to create pi orbitals by interacting the p orbitals and creating a linear combination thereof. So if we interact the p orbitals on each of those 4 carbons so that they all interact in phase, we will get one orbital extending over all 4 nuclei that's bonding with respect to carbon 1 and carbon 2, with respect to carbon 2 and carbon 3, and with respect to carbon 3 and carbon 4. So there are 3 net bonding interactions. And that's a nice low energy orbital. The electrons like to be able to spread out all over all 4 nuclei. We can create a second pi orbital by putting a node down the center and having the sign of the wave function change as you go across that node. And you'll notice that this has net bonding interactions with respect to carbon 1 and carbon 2, and with respect to carbon 3 and carbon 4, but it has an anti-bonding interaction with respect to carbon 2 and carbon 3. So it actually has just one net bonding interaction. Got still a net bonding orbital though. So these two are both bonding orbitals, and they'll both be lower in energy than the original p orbital energy level. So let's put that p orbital energy level here. These are the 4 2pz orbitals, each of which has 1 electron in it, 1 methane. And we don't have to put the node through a nucleus like we did with the odd number, because the center of the molecule is now a bond, not a nucleus. The other 2 orbitals are going to be anti-bonding, and in order to be symmetrically distributed about the original 2p energy level, so that they satisfy the requirement that the sum of the energies of the bond of the molecular orbitals has to be equal to the sum of the energies of the atomic orbitals, they will have to be 1 net anti-bonding and 3 net anti-bonding interactions. As we go up in energy, number of nodes increases. And it turns out that the number of nodes is always one less than the number of the orbital. So pi 1 has 0 nodes, pi 2 has 1 node, pi 3 has 2 nodes, and pi 4 will have 3 nodes. You'll notice that pi 3, which is antibonding, has 2 antibonding interactions with respect to carbon 1 and carbon 2 and carbon 3 and carbon 4, but it's net bonding with respect to carbon 2 and carbon 3. So this has 1 net antibonding interaction. Overall, these are 2-node orbital. And then pi 4 will have nodes between all of the nuclei and will look a lot like uninteracting d orbitals, except that it will be a little bit skewed like the pi star orbital. And it has net antibonding interactions with respect to every set of 2 adjacent carbons, or 3 net antibonding interactions. So they're symmetrically distributed about the original energy level. And if we wanted to put that on an energy diagram, we could represent it like this. They'll be approximately evenly spaced. And pi 1 will be the same amount below the original P energy level as pi 4 star is above, and pi 3 star will be the same amount above as pi 2 is below. Hopefully I have that approximately to scale. And now these 4 electrons can be put in using the alpha principle. The gap between pi 1 and pi 2 is much larger than the spin pair energy, so the second one will go here. And we have a bond order of 2. Because we have 4 bonding electrons and 0 antibonding electrons, and the bond order is always equal to the number of bonding electrons minus the number of antibonding electrons divided by 2. Right? A bond order of 2, 2 pi bonds, that's what we see in the structure. You'll notice that the structure as written looks a lot like pi 2, which is the HOMO, the highest occupied molecular orbital. The LUMO, by contrast, actually looks like a resonance structure that has a single electron on each end and a pi bond between the 2 center carbons. These are resonance structures. You're normally not going to write that resonance structure because it's a poor resonance structure with unpaired electrons and unfilled octets on the carbon. But the lowest unoccupied molecular orbital, or pi 3, looks kind of like that. And pi 3, this lowest unoccupied molecular orbital, will actually be relevant in some reactions of this conjugated dieting system. But normally, it's the highest occupied molecular orbital that's going to be involved in donating the electrons from the pi system to an electrophile of some sort. So if we were to add HBr across this molecule, we would expect the pi bond to attack the hydrogen. Generate a carbocation intermediate, and we would expect it to react on the ends of the system those reacting at the end of the pi system yield an allylic carbocation that has a resonance structure that stabilizes that positive charge and still has an extended pi system, but a 3-orbital extended pi system now instead of a 4-orbital extended pi system. This is an unsymmetrical system. One end of the allylic system is a secondary carbocation, the other end is a primary. So we would expect a larger partial positive on this carbon because of the extra methyl group stabilizing it by hyperconjugation, but this is the more stable double bond. Because it's more substituted. Adding the bromine to one of those carbons will result in 2 different products. And we might expect to see one or the other of those products dominant, depending on whether we run the reaction at low temperature, under thermodynamic control, or under high temperature, low temperature under kinetic control, or higher temperature under thermodynamic control. And that is indeed what we see. If we run this at 0 degrees, we get approximately 70% of the secondary bromide. If we run this at a higher temperature, same reaction. Raising the temperature to 40 degrees C, our products are identical. But we now only see 15% of the secondary bromide and 85% of the primary bromide. So what we're thinking here is a higher temperature reaction under thermodynamic control, where the more stable product is the dominant. And equilibrium is reached. Both of these reactions have an allylic bromide, and heating either of these 2 allylic bromides will result in the same 85% to 15% mixture, because the bromide can fall back off and regenerate the allylic carbocation. At the lower temperature, we have a kinetically controlled reaction. Where the dominant product is the one that's more easily formed. There's a lower energy of activation for the negatively charged bromide attacking carbon having the larger partial positive charge will be the one with the greater substitution. So that will be the dominant pathway. And if the temperature is kept low enough, if the bromide doesn't fall off to regenerate the allylic carbocation, it will stay there at the secondary bromide. Whereas at a higher temperature, we can have the bromide fall back off to generate the allylic carbocation again, and that's resonance stabilized. The bromide ion can now attack the end carbon to generate the more stable product. We've seen thermodynamic and kinetic control before in the context of enolates, where the most accessible hydrogen is taken off at very low temperature with a hindered base like lithium diisopropylamide to generate the less substituted product on alkylation. But when we use a weaker base like an alkoxide or hydroxide and allow equilibrium to be reached, we get the more substituted alkylation product. This is just another example of the same thing, where thermodynamically controlled reactions give the product with a lower enthalpy of formation, the more stable product, double bond that's more substituted, whereas under kinetic control, the product that has a lower activation energy and is formed more easily is the dominant product. And in both cases, if we heat up, as I said, one of the bromides, we will get this 85 to 15% mixture through the intermediacy of the same allylic carbocation. So we definitely want to attack the diene, or have the diene attack at one of its ends to generate a carbocation that's allylic, and then by controlling the temperature, we can sometimes control which product we want. It's sometimes not possible because there may not be a very large enthalpy of formation difference, and so you'll get a complicated mixture of products. Dienes obviously can add many of the same electrophiles that ordinary alkenes can add, as can trienes. So if we were to take 1,3-butadiene and add bromine and dichloromethane, we would expect to get a mixture of the 1,2 addition product, which again should be kinetically favored because the bromine, the second bromide ends up at the carbon that's more substituted and has the larger partial positive. But we would also expect to get a significant amount of the 1,4 addition product, this is the thermodynamic product. And I can't actually remember what the ratio of these two products is, but it's much more equal than the ratio we saw with the addition of HBr between the 1,2 and the 1,4 addition product. Again, this is the more stable of the bond, but this is the one with the larger partial positive, which means the more stable of the, or the dominant resonance structure of the resonance hybrid. So what we want to do in the next couple of videos is extend this pi system still further to a 5 pi orbital system or a 6 pi orbital system.